So welcome back to Chemical Equilibrium. So in this lecture, we're going to continue our discussion and try to continue our discussion on solving equilibrium problems. So yesterday in the last lecture, we discussed that whenever you have equilibrium quantities, we generally substitute these into the expression for the equilibrium constant and calculate its value. Now, if only some equilibrium quantities are given, we generally use what we call as a reaction table to calculate them and find the value. So how do you use the reaction table? So generally reaction table shows mainly four things. One, the balanced equation, the initial quantities of the reactants and product, the changes in these quantities during the reaction, and finally the equilibrium quantities. So let's take an example. So in a study of carbon oxidation, an evacuated vessel containing a small amount of powdered graphite is heated to 1080 Kelvin. Gaseous carbon dioxide is added to a pressure of 0.458 atmosphere and carbon monoxide forms. At equilibrium, the total pressure is 0.757 atmosphere. Calculate Kp. So first, let's try to draw the reaction table. So we have carbon dioxide, which is the gas, combining with carbon, which is graphite, creating carbon monoxide, which is a gas. Now to balance this equation, we can just write 2CO. Now this is the initial part. So what is the next one? So try to write three main things: the initial value, the amount of change, and the equilibrium point. So it said that initially the carbon monoxide is added to a pressure of 0.458 atmosphere. So this carbon monoxide has a pressure of 0.458 atmosphere. Now let's consider that notice that graphite is solid, so we can always write it as a dash. So remember that these are not considered while calculating equilibrium constant. Let's consider that in the formation of carbon monoxide, there is a decrease of pressure. So notice that initially there's 0, which means that there is no change in the amount of carbon monoxide because initially there is no product formation. Now let's consider there is a change of negative x. Notice that for each one value here, 1 mole, there is 2 moles of change here. So which means that if this undergoes negative x, this becomes plus 2x. And in terms of the equilibrium, you will get 0.458 minus x, and this becomes 2x. Now, so the next thing you have to remember is given the value here is the total pressure, which is 0.757 atmosphere. So which is the pressure of carbon dioxide plus the pressure of carbon monoxide. So the combined pressure of carbon dioxide and carbon monoxide is given as 0.758 atmosphere. Now the equilibrium pressure at carbon dioxide is 0.458 minus x plus 2x equals 0.758. So 0.458 plus x equals 0.758. X becomes 0.758 minus 0.458. So that value gives you 0.300 atmosphere. So this is the x value that you have found out. Now we have calculated the x value. The next thing we need here, the value is 0.757. So this becomes 0.299. Now, how do you find Kp? Kp is the product square. So product here is PCO square over PCO2. So we need PCO. PCO is 2x, so which is 2 times 0.299 square divided by PCO2 is 0.458 minus 0.299. So the final value gives you a total value of 2.25. So this is the value of Kp, which is 2.25. So this is how you solve a problem involving the changes here. So first remember that we need the balanced equation. Based on the balanced equations coefficients, we generally can determine the amount of values that are left here. So let's try another problem. So in order to study hydrogen halide decomposition, a researcher fills an evacuated 2-liter flask with 0.200 mole of HI gas and allows the reaction to proceed at 453 degrees centigrade. So what's given here? 2HI gives you H2 plus I2. At equilibrium, the HI concentration is given. They're asking you to calculate Kc. Now, we need to know the initial concentration of HI. What is given here? So you have an evacuated 2-liter flask with 0.200 mole of HI gas. So the concentration of HI in the initial value is the number of moles by volume. So the number of moles is 0.200 over 2 liters. So that becomes 0.1 m concentration of HI. Now the next thing, it's also given that HI has an equilibrium concentration of 0.078 mole. Now again, use the reaction table. So you have 2HI, which is a gas, decomposing to form H2, which is a gas, plus I2, which is a gas. So let's consider initial, change, and final. Now notice that initially HI has a concentration of 0.1 m, and H2 and I2 have a concentrations of 0, because remember that these are the products. Now change, notice that this is twice the amount. So if this reduces by twice, this will only increase by once. So this is a 2-to-1 ratio. So which means that if this decreases by twice, this increases only by once. So the final value, or the equilibrium value, is going to be 0.1 minus 2x, and this is going to be x and x. Now they have also given the equilibrium concentration. So notice that this value is equal to this value right here. So it's given that the HI equilibrium is 0.078 m. So HI equilibrium is 0.1 minus 2x equals 0.078. So 2x becomes 0.1 minus 0.078. So 2x becomes 0.022. X becomes 0.011 m. Now let's consider the final value. Then we need Kc. So we know the formula for Kc is going to be taking the equation. So from the equation what we have, so it's the product concentration by the reactant concentration. So product concentration is H2 times I2 divided by HI square. H2 is x times x by HI square is 0.078 square. So x we have already found out, which is 0.011 times 0.011 over 0.078 square. So the final value becomes 0.020. So this is the value for Kc, the equilibrium constant for concentration. So this is how you determine the value for Kc. So let's try another problem. Here what is given, you have in a study of conversion of methane to other fuels, the chemical engineer mixes gaseous CH4 and H2O in a 0.32 liter flask at 1200 Kelvin. At equilibrium, the flask contains 0.26 mole of carbon monoxide, 0.091 mole of hydrogen, and 0.041 mole of CH4. What is the H2O at equilibrium? So they have given Kc for the process at 1200 Kelvin. So write down the values right here. Notice the flask volume. So first we need to find the concentration of CH4, the concentration of H2, and the concentration of CO. So the concentration of CH4 is 0.041 mole divided by 0.32 liters. Again, H2 is 0.091 mole over 0.32 liters, and carbon monoxide is 0.26 mole over 0.32 liters. Now, the carbon monoxide value becomes 0.81, H2 value becomes 0.28, and CH4 value becomes 0.1. So these are the concentrations. Next, we have to write down the reaction. So CH4 and H2O mixes together to form CO plus H2. So to balance the reaction, we notice that the hydrogens, the carbon and oxygen are already balanced. There are 6 hydrogens, so we can write 3H2O. So from this, the only thing that we do not know here is H2O concentration, but they have given us Kc value, which is 0.26. So now let's write down the formula for Kc. So the formula for Kc for this reaction here is CO CO times H2 cube over CH4 times H2O. So from this, if you reshuffle the equation, and that becomes H2O concentration becomes CO times H2 cube over CH4 times Kc. So CO here is 0.81 times H2 concentration is 0.28 cube over CH4 concentration is 0.13 times 0.26. So when you multiply the whole values, you end up with the concentration of 0.53 mole. So this is the concentration of H2O in that solution. So use the same principle now. Pause the video right here. Notice that here, what is given here is that fuel engineers use the extent of change of CO and H2O to CO2 and H2 to regulate the proportions of synthetic fuel mixtures. If 0.250 mole of CO and 0.250 mole of H2O gases are placed in a 125 ml flask at 900 Kelvin, what is the composition of the equilibrium mixture? At this temperature, Kc is 1.56. So notice that they have given us the initial values. So we need to calculate. Notice the equation here is CO and H2O combining to form CO2 plus H2. So notice that the equation is already balanced, so we don't need to balance it again. So you have CO concentration, H2O concentration given. So notice that these are the initial concentrations. So which is also again number of moles by volume. So the number of moles is 0.250 with a 125 ml flask. So 0.250. So 125 ml can be written as 0.125 liters. And H2O concentration is 0.250 over again 0.125. So this can be written as 2 molar each. So this is 2m and this is 2m each. So these are the initial concentrations. So now let's try and write the reaction table for this. So CO plus H2O gives CO2 plus H2. So you have initial, change, and equilibrium. CO is 2.00, H2O is 2.00, and initial values of these two are 0 and 0. Now the change, if you consider that this decreases by x, this also decreases by x. Notice that this is a 1-to-1 ratio for all of them, so which means that this increases by plus x and this increases by plus x. So the equilibrium value becomes 2 minus x and 2 minus x. This becomes x and x. Now what is given in the question? So they've given us Kc value. So Kc value for the equation that we have right here, what would be the Kc? Concentration of CO2 times concentration of H2 over concentration of CO times concentration of H2. Concentration of H2 over concentration of CO times concentration of H2. So Kc is initially given as 1.56 equals CO concentration is X times X over 2 minus X times 2 minus X. So 1.56, which can be written as X square over 2 minus X whole square. Now this can be written as X by 2 minus X whole square is equal to 1.56. So when you square root on both sides, you get X by 2 minus X becomes under root 1.56. So this is can be written as plus or minus. Remember that square, when it goes that side, it becomes plus or minus. So plus or minus root 1.56 can be written as plus or minus 1.25. So X by 2 minus X can be written as plus or minus 1.25. So there can be two answers, X by 2 minus X becoming plus 1.25 or X by 2 minus X becoming minus 1.25. So X becomes 1.25 times 2 minus X, and here becomes X becomes minus 1.25 times 2 minus X. So X becomes 1.25 times 2 minus 1.25X. So here X becomes minus 1.25 times 2 plus 1.25X. Now, based on these values, so X can be 2.50 minus 1.25X, or X can be minus 2.50 plus 1.25X. Now, if 2.5 goes this side and X goes to that side, you get 1.25 X minus X is equal to 2.50. Here, let's bring the 1.25 this side. So that becomes 2.25 X becomes 2.50. So here it becomes 0.25X becomes 2.50. So X becomes 2.50 by 2.25. X becomes 2.50 by 0.25. So based on the values that we have right here, if you calculate the values, now, so when you calculate using this value, you get a X value of 1.11, and here you get X value of 10. But notice that here, X generally cannot exceed the actual concentration, the initial concentration, so which means that this is not applicable. So this is the only answer. So if X is 1.11, we can write that 2.00 minus X becomes 0.89 m. So they have given us everything. First thing that we need to find here is the initial concentrations of each and every one of them. So the equilibrium concentration of CO is 2 minus X, H2O is 2 minus X, CO2 is X, and H2 is X. So from this, we can write that the concentration of CO2 is 1.11 m. The concentration of H2 at equilibrium is 1.11 m. The concentration of CO at equilibrium is 0.89 m. The concentration of H2O at equilibrium is 0.89 m. So these are the answers for the values, and this is how you find. Even if you get two answers, see that the value does not exceed the initial concentration. So that's how it cannot be more than the initial concentration, as well as it cannot be negative. So those are the two things to remember. So use the same principle now. Pause the video right here and try to solve these problems. Next, let's go to the topic of the simplifying assumption. So we generally consider that the term X times the concentration, reactant concentration of the reactant can be neglected, provided that Kc is relatively small and the initial concentration is relatively large. So these are the two cases where we consider. So provided that the ratio of the initial concentration to the Kc is generally greater than 400, then we can assume the assumption is justified, so meaning that neglecting X introduces an error of less than 5%. Now, if you do have a value of less than 400, the assumption is not justified, thereby neglecting X introduces an error of 5%. So let's take an example problem. So what is given here? The research and development unit of a chemical company is studying the reaction between CH4 and H2S and two components of natural gas. So which is CH4 plus H2S gives you CS2 plus 4H2. In one experiment, 1 mole of CH4, 1 mole of CS2 and 2 moles of H2S and 2 moles of H2 are mixed in 250 ml vessel at 960 degrees centigrade. At this temperature, the value of Kc is given. So what are they asking you to do? So in which direction will the reaction proceed to reach the equilibrium? And number 2, if the CH4 is 5.56 molar at equilibrium, what are the equilibrium concentration of the other substances? So let's take into consideration each of these concentrations and let's try to find the values first. Now, how would you calculate the concentration? How would you calculate the reaction direction? Is based on the initial concentrations, we can find the value of Qc and we can compare Q with Kc and then determine the direction in which the reaction goes. And then using the reaction table, we can find the concentrations of other substances. So let's first write down the reaction. CH4 plus 2H2S gives CS2 plus 4H2. Now, so we have to find the initial concentrations of CH4, the initial concentration of H2S, the initial concentration of CS2, and the initial concentration of H2. So again, the same formula applies, number of moles by volume. So the amount of CH4 is 1 mole over the volume is 250 ml, so it becomes 0.250, and H2S is 2 mole or 0.25. CS2 is 1 mole and H2 is 2 mole. So this becomes 4.00 m, and this becomes 8.00 m, this becomes 4.00 m, and this becomes 8.00 m. So these are the initial concentrations. From the initial concentrations, find Qc. Formula for Qc can be written as concentration of CS2 times concentration of H2 to the power 4 over concentration of CH4 times concentration of H2S square. Notice that all of them are initial concentrations. So CS2 is 4 times H2 is 8 to the power 4 over CH4 is 4 times 8.00 square. Square power 4 gone. So you get a value of 8 square, which is 64. So Qc is 64, and from the formula Kc is 0.036. So Qc is greater than K. So notice that because Qc is greater than K, which means that Qc tries to go towards K. So when Qc tries to go towards K, the one thing that reduces here, notice that the concentration of the products should decrease and the concentration of the reactant should increase. So which means that here it goes towards the left, so which means the reaction goes towards the reactants. So the direction, the reaction is towards the reactants. So we have Qc greater than K. Now the next one is given as CH4 concentration at equilibrium is 5.56. So first let's write down the reaction table. Initial change and equilibrium. So because the reaction is going towards the reactants, which means that the reactants are going to increase and the products are going to decrease. So what are the initial concentrations given here? So CH4 initial concentration is 4, H2S is 8, CS2 is 4, and H2 is 8. Now, in terms of the change, the ratios are 1 to 1, 4. So notice that there is a reaction is directed towards the, so the reaction here is directed towards left, which means that the reactants are going to increase and the products are going to decrease. So which means that there is a reduction in the products and increase in the reactants. So which means that this undergoes a change of plus x. If this undergoes plus x, notice that this is once, so which means this undergoes twice, plus 2x. And CS2 is going to undergo minus x and H2 is going to undergo minus 4x. So from this, equilibrium can be written as 4 plus x, 8 plus 2x, 4 minus x, and 8 minus 4x. So the equilibrium concentration of CH4 is given, so in the problem, which is 5.56 mole. So CH4 equilibrium concentration is, from this value we have 4 plus x, but the value is given as 5.56. So which is equal to 4 plus x. So x becomes 5.56 minus 4.00. So x becomes 1.56 gram. So from the x value right now, we have H2S concentration, we have CS2 concentration, and we have H2 concentration. So we found the CH4 concentration as 5.56 molar, the equilibrium. Now the next one is H2S concentration at equilibrium is 8 plus 2x, 8 plus 2 times 1.56. So when you calculate, that gives you a value of 11.12 mole. Next you have CS2 at equilibrium. So from the formula, CS2 is 4 minus x. So which is 4 minus 1.56, which is going to become 2.44 mole. And H2 at equilibrium is 8 minus 4x, 8 minus 4 times 1.56. So that value becomes 1.76 molar. So these are the concentrations at equilibrium, and this is how we can solve the problem. So remember that all the problems involve the reaction table. So once you are familiar with the reaction table, it becomes easier to solve problems. So try to solve more problems from the textbook. So these are the steps here in summary. So the preliminary setting up involves the balanced equation first. Next, writing up the expression for the reaction quotient. Finally, convert all amounts into the correct units, either molar units or atmosphere if it's a kp. Next, when reaction direction is not known, compare Q and K. If Q is greater than K, the reaction goes towards the left. If Q is less than K, the reaction goes to the right. And if Q is equal to K, the reaction is at equilibrium already. And finally, construct the reaction table. Check the sign of X and change in the concentration. Now, if you have initial minus x equals to equilibrium constant, so the x value is, if it is minute, we can write it nearly equal to the initial concentration. I'm sorry. This is x times the equilibrium concentration. So we can write it as the initial concentration based on the justification that if you have a less than 5% error. And finally, find the equilibrium quantities. So with that, we end the topic on how to solve for equilibrium problems or equilibrium constants. So let's continue our lecture and let's talk about the Le Chatelier's principle. So what does the Le Chatelier's principle say? So it says that whenever a chemical system at equilibrium is disturbed, it reattains equilibrium by undergoing a net reaction that reduces the effect of that disturbance. Now remember this point here, that it generally, by undergoing a net reaction, that reduces the effect of that disturbance, which means that the system tries to move back to equilibrium. So a system is disturbed when a change in conditions force it temporarily out of the equilibrium. Now the system responds to a disturbance by generally a shift in the equilibrium position. So the equilibrium position generally, for example, there can be two types. One of them is a shift to the left, which means that the net reaction will be towards the reactant from the product, and to the right represents the net reaction from the reactant to the product. So these are the two types of shift that generally occur. So let's take an example. So let's talk about the first effect, the effect of change in concentration. Now let's consider a reaction where you have A to B. Now if the concentration of A increases, the system reacts to consume some of it. So which means that if you add a reactant, the equilibrium position shifts to the right. If you add a product, the equilibrium position shifts to the left. So when you add a reactant, it shifts to the right, which means that when you add a reactant, it increases the product. When you add a product, it increases the amount of reactant. So these two are the ones that generally occur. Now when you decrease the concentration, the system reacts to consume some of it. So which means that when you remove the reactant, the equilibrium position shifts to the left. So when you remove the reactant will increase, the product will decrease. When the product is removed, the equilibrium position shifts to the right. So which means that when you remove the product is increased, the reactant undergoes a decrease. Now only substances that appear in the expression for Q can have an effect. So which means that change in concentration has no effect on the value of Q. Remember this, it only has effect on Q but not on K. So for example, when you increase PCl3 and Cl2, it decreases the amount of PCl5. Now when you increase PCl5, it decreases the amount of reactant that is present. So these are any changes that can cause a shift to the right. Any of these changes generally can cause to the shift to the left. So let's take an example. What is given here? To improve air quality and obtain a useful product, chemists often remove sulfur from coal and natural gas by treating the containment hydrogen sulfide with oxygen. You have H2S plus O2 gives 2S plus 2H2O. So what is given here? What happens to the concentration of H2O if O2 is added? O2 here is the reactant. When you add reactant, it means that the reaction will try to adjust it in such a way that the reactant will try to adjust itself. So think about it like a balance, where one side you have the reactants and one side you have the products. So which means that now when you add reactant, so what is happening here is that the reactant, this one will go down. So which means that this will go up. Now to oppose this motion right here, what will happen now is that when the reactant goes down, so when you are pushing it downward, so to adjust the reaction, what will happen here, the product also will come down. So which means the product will try to increase. So notice that H2O is the product, so which means that H2O will increase when you add the reactant. Now what happens to O2 if H2S is removed? So let's say H2S if your O2 is added. So when you increase the oxygen, the reaction moves to the right, which means that this generally decreases. So H2S will undergo a decrease. Next, when you remove H2S, so H2S is the reactant. What happens to the oxygen right there? Oxygen tries to increase to adjust to the reaction right here. So Q increases, therefore the reaction proceeds to the left. So until QC becomes equal to KC. So remember the formula QC. This is the one that gives you the entire part. Next, the last one, H2S if sulfur is added. Notice that sulfur is not in any of the QC equations, so which means that it does not have any effect on the equilibrium. So H2S is unchanged. Next, let's talk about the effect of change in pressure. Now, change in pressure affects the equilibrium system containing gaseous components only. So, changing the concentration of gaseous components causes the equilibrium to shift accordingly. So, which means that whenever you add an inert gas, there is no effect on the equilibrium. Now, changing the volume of the reaction vessel will cause equilibrium to shift, provided that delta N of the gas is not equal to 0. Now, changes in pressure or volume have no effect on the value of K. Remember this point again. pressure and volume do not have any effect on the value of K. So when you have a lower pressure, it means that there is a higher volume. So the equilibrium shift to form more molecules of the gas. So which means that it goes towards the side that has more number of moles. Here if you take the reaction, it has more number of moles on the reactant side. So it tries to go towards that side. Now when you have higher pressure and lower volume, the equilibrium shifts to form fewer molecules, which means it goes towards the side that has fewer number of moles. Here the product. Next, let's take an example here. How would you change the volume of each of the following to increase the yield of the products? Now notice that there are 2 moles of reactants, the products here, and 1 mole of reactant. Now, first things first, remember that when you have to increase the number of moles, you are going to lower the pressure, so which means that we are going to increase the volume. So you have to decrease the pressure to increase the volume. Only then it will go towards the side that creates more number of molecules. Now, when you want to increase the product here, you're going to go towards the side that has lower number of molecules, which means that we have to decrease the volume and increase the pressure. And the last one again, notice that both sides have the same number of moles, so there is no effect of pressure and volume. So notice that because they have the same number of moles on each side, so which means that there is no effect of changing in the pressure or volume. Next, let's come to the last one, which is the change in temperature. Now, to determine the effect of change in temperature on equilibrium, we consider the heat component of the system. Now, remember that heat is the product in an exothermic reaction and heat is the reactant in an endothermic reaction. Now, an increase in temperature generally adds heat, which favors the endothermic reaction. A decrease in temperature removes heat, which favors the exothermic reaction. So remember this, when you increase the temperature, it favors the endothermic reaction. When you decrease the temperature, it favors the exothermic reaction. Now, temperature is the only quantity that can affect the value of the equilibrium constant. So when you have a reaction that is endothermic, where delta H of the reaction is greater than 0, and an increase in temperature will generally cause K to increase. Now, when you have an exothermic reaction and an increase in temperature, K will decrease. So when it is endo and the temperature increases, K will also increase. When it is exothermic and the temperature increases, K will undergo a decrease. Now the Van Hoff equation generally shows this relationship written by ln K2 by K1 equals negative delta H reaction by R times 1 by T2 minus 1 by T1. So let's take an example here. So how does an increase in temperature affect the equilibrium concentration of the underlying substances for each of the following? Now they have increased the temperature. So first things first, remember here that delta H here, this is an exothermic reaction. This is endo, this is also endo. Now when you increase temperature, it favors the exothermic reaction, which means that it favors the product. So it means that the reaction goes towards the right. So remember this point that whenever you have a decrease in temperature, an decrease in temperature favors the exothermic reaction. So which means that, here decrease in temperature, there is an increase in temperature, which means it favors the endothermic reaction, which means the reverse, it favors the reactants. So which means that the reaction goes to the left. So the reaction will go towards the left and thereby causing the K value to decrease. Notice that because it is exo and there is a temperature increase, so which means that the K value will decrease. Next, the second one, you have CaCO3 plus heat giving you CaO plus CO2. Now in this, the second one, it's an endothermic reaction and there is an increase in temperature. So an increase in temperature always favors the endothermic reaction, which means the reaction goes towards the right. Now because it's endo and temperature is increasing, the K value will also increase. So K will also increase. Next, you have the last one, SO2 giving you sulfur plus oxygen. Again an endothermic reaction where there is a temperature increase, which means that K value will also increase. Now higher temperature favors the endothermic reaction, which means that the reaction goes to the right. So towards the product. So this is the way we predict the effect of change on equilibrium. Next, last one is catalyst. Now catalysts only change the chemical kinetics, which means they generally speed up the reaction by lowering its activation energy. A catalyst therefore speeds up the forward and reverse reactions to the same extent. Now, a catalyst causes a reaction to reach equilibrium more quickly, but generally does not have any effect on the equilibrium position. So either adding a catalyst or removing the catalyst does not change the equilibrium position. So this is the final concept, entirety of the entire change. So again, when you increase the reactant, it goes towards the product. When you decrease the reactant, it forms more reactant. When you increase the product, it goes to form more reactant. When you decrease product, it forms more product. Finally, increasing pressure goes towards the fewer number of moles. So when you increase pressure, it goes towards creating lower number of moles. When you decrease pressure, it goes to creating higher number of moles. And when you add an inert gas, there is no change in the concentration. Next, finally, temperature. Temperature is the only quantity that can have an effect on the value of K. Now, increasing the temperature goes towards absorption of heat. Decreasing the temperature goes towards release of heat. Now, K value increases under an endothermic reaction and decreases under an exothermic reaction. When you decrease temperature, it increases in an exothermic reaction, and decreases in an endothermic reaction. Finally, catalysts do not have any effect on the rate on the equilibrium position. So they only change the forward or backward reverse rates of a reaction. The only thing that it can do with equilibrium is that it will help the reaction to achieve equilibrium sooner. So pause the video right here and use the principles that we discussed right now and try to solve this problem. So next, let's come to the last topic, the synthesis of ammonia. So ammonia is synthesized industrially via the Haber process. So the reaction involves N2 and hydrogen and hydrogen combine to create NH3. Now notice that the reaction is exothermic. Now there are three ways to maximize the yield of NH3. So we have to increase the product. One way is to decrease the amount of product by removing the product. So when you decrease the concentration of NH3 when you remove NH3. Second is to decrease the volume, thereby increases the pressure, thereby resulting in fewer number of moles. So when you decrease the pressure and increase the volume, it goes towards the side that decreases the number of moles. Next, finally, decrease the temperature. Now, when you write it into a table in terms of the Kc values at given temperatures, you start noticing that the value becomes lower and lower as you go towards higher temperatures. Now, you can take a graph of yield to temperature with pressure curves in them. So the optimal conditions that are generally used are around 200 to 300 atmosphere at around 400 degrees centigrade. This is the industrial conditions that generally produce a yield of around 40%. So this is the one that is commonly used in the industry as a standard procedure. So this is a diagram that shows you the key stages in synthesizing ammonia. Remember that we are trying to remove NH3, so which means that we condense ammonia to the point where we remove some of the ammonia and thereby send back the remaining amount of H2 and N2 back into the compressor to react with the chamber in the catalyst bed, resulting in the formation of again the ammonia H2 N2 mixture, resulting in this cycle formation again. So this is how the Haber process generally occurs. So with that, we end the lecture on chemical equilibrium. I will see you again in the next lecture.